A sample of 500 grams of a radioactive lead decays to polonium-210 according to the function A of t equals 500 e to the negative 0.032 t, where t is time in years. How much lead is left after 5 years? In order to answer that question, we look at our growth model. And the growth model here is given in the problem. So the amount that's of radioactive material present after a specific amount of time is the initial amount of 500 grams times e to the negative 0.032 times t. So if we want to know how much is left after 5 years, all we need to do is plug into our growth model where t is equal to 5. So this would be 500 e to the negative 0.032 times 5. Now, using our calculator, we can come up with an approximation for what that value is. And the way we would do that is just type in 500, then e, then an exponent. And you may have actually gotten a caret key on screen. Just depends on what model calculator you have here. If you have a caret on screen, make sure you put parentheses around your exponent so that the multipliers, negative 0.032 times 5, are all up in your exponent. So here I'm just going to put in negative 0.032 times 5 and press enter. So that gives me 426.07 grams. Let's just round to 2 decimals because I don't think it's dated. So 426.07 grams remain. So this is decaying, so the amount of material is going away as time passes. So if about 75 grams decayed away after 5 years, the question is how much is going to decay after 20 years? Well, the expectation would be, since this is approximately 4 times the amount of time, that we would think that it would be 4 times 75 grams, or around 300 grams. Well, let's see what happens. So the amount left after 20 years is going to be 500 e to the negative 0.032 times 20. And I think I'm going to use an older calculator just so those of you using the older style calculator can see how to do the exponents properly. Alright, so we would still put 500 and then second and divide gives me the e. Then when I hit the exponent key, I need to make sure I use parentheses around the exponent. So negative 0.032 times 20. And then close parentheses so that the calculator knows that everything in this multiplication is part of the exponent. So that gives me 263.65 grams, it looks like. 263.65 grams. Now, the estimation that we made, since it's 4 times the amount of time, and there was about 75 grams taken away after the first 5 years, then there should have been about 300 grams taken away after 20 years if the growth was linear. And so, of course, 500 minus those 300 grams would put us at around 200 grams remaining. But the thing is, the growth isn't linear. The growth is exponential. So the growth changes as time goes on. So that's why not as much decayed away as we expected. The question then, in part C, asks, what's the half-life of the lead? Well, the half-life is the amount of time it takes for half of the material to decay. So let me just write that in. So the amount of time for half of the material to decay. Okay, so half of the material, if we started with 500 grams, then we want to end with 250 grams. So I'm going to set my model equal to 250 because then that way I can solve for the amount of time it's going to take to decay to that amount. So 250 equals 500 e to the negative 0.032 times t, which is the amount of time that I want to learn. So I've got a variable in the exponent, and I'm going to need eventually to get that out of the exponent, which means I'll change to a logarithm. But I can't do that until I just have the exponential function by itself. So I start off by getting rid of this 500, just dividing it to the other side. So 250 over 500, it's no mistake, that's a ratio of a half because we said it's a half-life. All right, so equals 0.032 times t. Now at this point, what we can do is we can change this exponential equation into logarithmic form so that we can solve for the variable. So in log form, it would be a log base e, because e is the base of our exponential, of 1/2, and then logarithms are equal to the exponent, so then that would be equal to the exponent negative 0.032 times t. So this is my equivalent log form of this expression. And of course, separate here. Log base e we know to be the natural logarithm, so I'll just write that as ln of 1/2 equals negative 0.032 times t. And then all I would need to do is divide that value by negative 0.032. So the amount of time would be the natural log of 1/2 divided by negative 0.032, and using the calculator I can approximate that value. So the natural log of 1/2, or I could just have typed in 0.5, that's fine, divided by negative 0.032 gives me about 21.66 years. I'll just keep doing 2 decimals here.